that's why we need to split our data set in several parts, because all the machine learning models are generated only on the data. So there are data-driven methods, and we need to split the data to train and evaluate at the same time the models. And at the end, we need to have a similar behavior in the training dataset and in the validation and test sets in order to have some confidence in the training. So how can we prevent overfitting? There are several techniques in the literature. We can expand or augment our data. We can control the model complexity with regularization techniques, validate and monitor the training. There are also a lot of techniques, and simplify the complexity of our data. The problem in astrophysics is that the observations are very expensive, and we cannot always increase our data set. And in a lot of cases, we don't want to use simulations, because in simulated data, always we have a theoretical model behind, so we want to avoid this bias. So this is a problem here. So for example, this is a small example for cosmology. Cosmology, some people is interested using Gaussian process or non-parametric techniques to reconstruct some cosmological functions given the data. So for example, in this case, we have a very small data set that are these green points with the error bars. And we are trying to, given the redshift, predict this function and the error. So using exactly the same architecture, you can see that if we train different number of epochs, we have different results. And this is very important because the physics of each figure is totally different. So you can say that the universe is expanding more or less, and how can you be confident of that? So in order to have a good architecture, the more basic technique is use a lot of combination of the hyperparameters. The hyperparameters of the neural network are all the settings that you need to fix before the training. So for example, the number of nodes, the number of hidden layers, the number of epochs, etc. And then we can explore all the combinations and then keep the one that minimizes better the loss function. And for example, for this simple example, we can have a little bit more confidence on this reconstruction than in the others. And also we can, for example, contrast this data-driven model with other theoretical cosmological models, and then analyze the discrepancy and the difference that exists between the real data, the theoretical models, and this data-driven model. And of course, we always in deep learning need to analyze the behavior of the loss function and see if the trend of the training set is similar to the one in the validation set. Even more, we have more advanced techniques to improve our deep learning trainings. So for example, the dropout is a very powerful and simple idea that it's very common as regularization technique. So to avoid overfitting, in which some few random nodes are randomly turned off during the training. So it's like an average of models at the end, and it produces better training. And it's very simple, very powerful. Maybe if you copy and paste some example from a Python library you are using it. And there is a very great variation of the dropout, that it's Monte Carlo dropout, in which some people suggested to use it not only during training, but also in the inference. So we already have a trained model, and then we turn off randomly some neurons during the inference. So instead to have a single prediction during the inference, we can have a set of predictions and have a type of posterior distribution of our predictions, and then get some information about the uncertainty of our method. That it's not, this uncertainty quantification is not something that it is by default in machine learning models, because one thing is the metric that we are minimizing, another thing is the uncertainty of the method. So that is why it's very important to consider this. And for example, in the same example, we can see the difference between considering the uncertainty quantification and without it. So we have a more smooth reconstruction, and also these error bars, each breadpoint here is an average of several predictions. So we can be sure that the variance of our trained neural network is not very high and have more reliable interpretations of our data analysis. And we can do this for different functions. For example, this other example is with cosmic chronometers. So we can directly model the whole function here, and then contrast with different predictions. For example, here we have the values of the tension of Hubble, a very famous cosmological problem, and then we can analyze the discrepancy of the prediction of the theoretical models with the data-driven model generated by the neural network. And of course, we need to analyze always those functions to be sure about that the things that we are doing are okay. And there are other techniques to do the hyperparameter tuning. I already explained the grid. We can use almost any optimization method. For example, genetic algorithms and all these algorithms that are included in the Octona library, that it's very easy to use. And in particular, I'm very interested in genetic algorithms because in this high-dimensional space of hyperparameters, it's good to have some methods that don't use derivatives and that only with the genetic operators that are based on natural selection, mutation, crossover, and stuff like that. We can involve initial random population of potential solutions and then find the best solution, even if we have multi-modes or stuff like that. Also in this paper, that it's also old, in 1994, there is also a demonstration that if we use the canonical genetic algorithm with a property called ellipticism, we always can find the global optimum. So this is very powerful, but also in this paper, they don't explain how you need to configure your genetic algorithm settings in order to have this. So it's theoretically possible, but you don't know how. Well, it's good to know. For example, in this work, we analyze these different regression tasks, modeling the observational data with neural networks, and finding the best configuration of the neural network with the classical grid hyperparameter optimization, and with different configurations of genetic algorithms. And in all the cases, we find that always the genetic algorithms have a better solution, minimizing better the metrics that we are interested in regression, and in a lower number of evaluations. So that's very useful because it's not always better in terms to have a good solution, but also you can save some time. Then, using all of these together, we apply all this procedure in other application. So for example, trying to accelerate Bayesian inference, in particular within the nested sampling framework, in which initially you sample n number of live points, collect these live points, and then you are sampling the posterior distribution, keeping in each iteration only the best individuals. And under that scheme, we train the neural network on the fly with only 100 or a few thousand of samples to try to learn the likelihood function. And we test it with toy models, for example, with the Xbox distribution. We compare the Bayesian evidence of the nested sampling with the neural network and only the nested sampling, and are quite similar. And then we also tested with a cosmological model, training on the fly. So the problem of our method is that in order to have precise predictions, we need to use the neural network near to the end of the Bayesian inference process, because otherwise we will have a lot of variance. We can save more time, but in not an accurate way. So for example, here we can see the comparison of posterior distributions for a very simple dark energy model with the neural network and without the neural network, and we can save around the 20% of time. So other applications, some colleagues were interested in these methods, and they applied the same idea to make data-driven methods, for example, using LSST supernovae simulations, and then compare the distance modulus with the theoretical predictions and with other surveys in order to analyze if the trend of this simulated data is similar to the existing surveys. And another colleague tried to perform data-driven models in rotation curves. And also she compared the data-driven models with the theoretical ones. And then, well, we can extend the application of these techniques. In all the previous examples, all the data sets are some dozens or 100, or in the best of scenarios, a few thousands of samples. And then we try to improve this big, to contribute to this big problem in exoplanet detection, that in order to detect an Earth-sized planet, we need to detect a tiny Doppler shift around of 10 centimeters per second. So using hard-snort data, we only have two thousands of spectra. We have a lot of stellar activity and high dimensionality of the data. So that's a problem. So the first challenge is the limited data. For that reason, we augment the data set, not with more observation because we cannot do that, but augmenting the data with the information that we want. So for example, instead of adding random noise, we add different combination of planetary injections on the data, and then we increase arbitrarily the size of the data set. And also in order to improve the physical information contained in the data, we use these previous works of some colleagues in order to represent not only the spectra of in terms of the flux, but also in the temperature, because some works show that it's more sensitive to the Doppler shift due to planetary presence. And to deal with the high dimensionality, we also use these other works in which some colleagues propose to use a gradient representation of the spectra, so we can convert these 300,000 wavelength spectra in tiny matrices of 9 by 9, for example. And for example, in this case, we can see this check representation without any Doppler shift. And when we inject a planetary signal, it's very sensitive to that. So using this representation, we convert our spectra in temperature, and we train our machine learning models with this configuration. Then our neural network architecture is quite simple. So we have as input the shells, then a traditional convolutional neural network, and then we are predicting the radial-velocity previously calculated by a cross correlation function, and the Doppler shift of the data augmentation that we are manually injecting. So traditionally, the CCF provides very good results, but the problem is that it mixes stellar, planetary, and instrumental effects. So this is a problem. That's why we are forcing to have an additional information here, that is something that the neural network, that the CCF cannot provide us by default. So we are forcing the models to learn that. And then we use all the techniques that we previously discussed here. So the hyperparameter optimization with genetic algorithm, the uncertainty quantification with Monte Carlo dropout, in order to have good prediction. So for example, in the CCF framework, we have the data, the spectra with a lot of wavelengths. Then we can do a line selection mask, compute with CCF the radial velocities, and then analyze the time series of the radial velocities in a CCF, and analyze if we have some peaks above some threshold in order to detect some signal. In our framework, we include the data augmentation, injecting arbitrary Doppler shifts with different periods. And then we convert we use the radial velocities to consolidate our training data. We compute the temperature given the flux, and we convert both the flux and the temperature in this shell representation. Then using the radial velocities, the Doppler shifts of the planetary injections, and the shells, we train the neural network model. And then instead to use the radial velocity values, we use the Doppler shift predictions in order to generate the parallelogram analysis. And to have more confidence in our results, we inject several planetary injections to the same periods and the same semi-amplitudes with different random phases. And if we have 7 of 10 successful detection, then we can consider that we are having a successful planetary recovery. So in order to train our models, we propose 2 different approaches. The first one was using a holdout method. So we only have 2,000 of spectra. So if we split 400, we separate totally them during the training. Then we augment the rest of the samples with the planetary injections. We train the neural network, and then we predict on the test set in order to test our model in unseen data. The problem here is that the parallelogram analysis is performed only in these 400 timestamps. So it can be very poor, but very realistic because in some cases we don't have more data. So it's good to test these kind of methods in small samples. And on the other hand, we also try a cross-validation approach in which we repeat the process in this case 5 times in order to have in each fault the same number of test set in each case. And at the end, we concatenate the predictions to cover all the time of the observations. So in this case, we can have the unseen predictions of the 2000 original spectra, and then we also compute the detection metrics. And then, for example, this is using these 10 random injections with a fixed period and semi-amplitudes. We can see here some results from 10 centimeters to 45, from 10 days to 550 days. This is with a holdout method, so all these predictions are only based on the analysis of 400 samples. And we can achieve some good values here, for example, at 25 centimeters, but only in the temperature case. So the results confirm that indeed the temperature representations have a better performance than the flux representation. That's something nice to see in the modeling with the neural networks. And if we do the same with the cross-validation method, we achieve even better precision. Even we can detect mostly all the 20 centimeters planetary injections here. And also the performance of the temperature representation is a bit better than with the flux. So of course we are using synthetic injections and solar data. So even with the real data, we have, of course, good conditions. The idea is to try to do this with other sources and real planetary signals, but it's quite promising at the moment. And only to illustrate better the process, for example, these are the two outputs of our neural network. And in this case, we have the 10 predictions with the 10 random phases injected at the same period, at the same semi-amplitude, in this case 20 centimeters and by second and 50 days. So for example, in this panel, we have the parallelogram of the traditional CCF radial-velocity and the prediction of the radial-velocity with a neural network. And we cannot detect anything around 50 days, neither with the classical CCF, nor with the radial-velocity prediction from the neural network. But if we analyze, if we make a zoom around the injected period in the Doppler shift predictions of the neural network, we detect the signal, and it is higher than the stellar noise that we have here. So that's something good because with the small planetary injections, it's very common to be dominated by this stellar activity. So seems to be working, and we also have this kind of steps, we can see the similarity of the radial-velocity predictions with the real values of the CCF, and also the phase recovery test here, that is pretty good. And then, okay, to conclude, and there are other approaches. I will show you only supervised learning at this moment. Well, we can use other architectures, for example, the autoencoder that is unsupervised. This kind of methods tries to reproduce the same output as input. And in the middle, we have a bottleneck with a compressed representation that if we use linear activation functions, this autoencoder is similar to a PCA, but with the difference that thanks to the nonlinear activation functions, we have a nonlinear modeling. And there are other works in which instead to have a discrete space here, we can take advantage of the random generation of the numbers and sampling the distribution of this latent space. And at the end of the process, we can know the posterior distribution of this latent space and extract probabilistic information of this compressed representation. In addition, we can add some conditions to these methods to constrain even more this latent representation. And for example, we are trying to use this with spectra data, with photometric data, and with the shell representation. So we can use as input and output the shells, constrain the latent space to 3 dimensions only, and then fit the conditional, add a condition during the training with a radial velocity and a Doppler shift. That it's not supervised because when we infer, we don't need this information. It's only to constrain the degrees of freedom of this sampling. And for example, the idea is to try to analyze if these different latent representation can have some physical information that we are interested to. For example, here we have the parallelogram of 3 different latent components in comparison with the radial velocity CCF, and we can't see anything here. But if we add the condition with the radial velocity and the Doppler shift injection to constrain more the latent space, we can recover a relatively high signal injection of 30 centimeters. That is something good, and something that we are exploring is the modeling of this part, that it's doing stellar activity. So maybe adding more conditions to the latent space, we can separate planetary signals from stellar activity. So this is a work in progress. And well, we are working now in trying to extend the CNN framework to other stellar systems and to validate it with real planetary signals. Also, the conditional variational autoencoder seems to be very promising, but it's we need to have a lot of work there because there is not a well-established framework to do a statistical analysis from the latent space. These kind of generative models are usually used only to generate images, not for do a statistical modeling of the data. So we're on that. Also, we are trying to generate models with deep learning and genetic programming of the magnetic activity to have interpretable descriptions of the stellar activity. And well, of course, the final goal is to include some of these machine learning tools for the upcoming plate mission. And well, some final remarks is that deep learning can be used in small astrophysical datasets if we use a proper regularization and hyperparameter tuning techniques that are not included by default in the library. So sometimes we need to use different Python libraries or even write some code from scratch in order to perform this properly. Also, if we introduce more physics in our data, we don't have the limitation to transform our data in any way that we want. So, for example, in the case of mapping the flux to temperature, we improve significantly the results. So we need to consider that. Also, generative models are very used in the large language models, in images, but I think that they offer a big opportunity to generate probabilistic models for our data. So I think that it's worth it to explore more this kind of algorithms. And finally, all of these techniques only work if we use them as complement of physics and classical statistical methods. Machine learning is not magic learning, is not a black box, and the goal of this technique is not to substitute traditional methods, is only work in conjunction of the very good and robust methods that we already have. And in such a way, we can try to improve some data analysis results that we have with our current limitations of the data. And that's all. Question? Yes.
Thank you so much. Very interesting. I was wondering, like, you have solved a big problem, which is the lack of data by using data augmentation. But sometimes it's kind of difficult to do this data augmentation, right? And here you have a physically motivated model. You can introduce the shape. I was wondering whether you have tried contrastive learning, for example, without the use of data augmentation. If you could comment on that.
No, I didn't explore that, but it's interesting one. Yes, I agree that it's not always possible. It depends a lot of the problem. Because, for example, in this work, the first attempt is to add, for example, Gaussian noise, and you miss all your data, so it's not always applicable, but yeah, it's interesting to explore also contrastive.
Thank you very much, Isidro, for this nice talk. I'm curious about the last part where you mentioned something about Plato. Can you explain a bit more, because I missed that part? How are you using Plato for this? How are you using this analysis for the Plato coming data?
Yeah, well, indeed, I'm in the stellar variability group. So we are trying to generate data-driven models for the magnetic activity. And the techniques are the same. So we are trying to use data networks to generate models instead to the early model, use data-driven methods, and at the end with a proper hyperparameter optimization and uncertainty quantification.
Okay, but the idea is not to search for planets using machine learning in Plato.
Not, but at the end, if we know more about if we know more about let me okay. If we know where is the magnetic activity field,
Okay.
we can improve the false detections in the planetary.
Well, Plato is using transit photometry instead of radial-velocity, so
Yeah,
it will be different.
but then we can constrain our models using this information.
Okay.
Yeah.
It's about the background, what we are studying in the background generated by stellar activity. So it's noise for planetary transits detections and noise for pulsation also.
Okay.
Yeah.
Thank you.
Thank you. Yes.
Thank you, Isidro. It's talk very interesting. I catch a part because I'm not very much in modeling and field, but I was very interested in one of your first slides where you talk about the dropout technique. Okay.
Sorry?
The dropout technique,
yeah.
the one in which you quit some
Yes.
some nodes, some neuron. Okay. Because you talk before of a random dropout. I mean, you catch one neuron and you take out randomly. I mean, you choose the neuron randomly. And then you talk about a Monte Carlo dropout, if I will understand.
Hmm?
No, it's no. Yeah, but then some slides after you talk about the Monte Carlo. I understand the Monte Carlo dropout. So you quit the neuron based on some energy consideration, no? Some objective function consideration or not.
No. For example,
I mean, in this case, you take out the neuron randomly. You choose a random neuron and you take out. But then some slides afterward, I read MCDO that I understand that is Monte Carlo power.
Yeah.
Okay, so you quit not randomly.
No, it's always random because at the end it's like all the sampling methods, like Bayesian inference, are based on the random sampling that you are constraining with some conditions. So at the end, if you don't turn off randomly these neurons, you cannot have a reliable distribution function of the prediction. So it's also
It's
random.
randomly, but following a function that is not usual. This is
Yeah.
Okay.
Yeah.
And then another thing that I want to comment is if does exist a technique of dropout based on the actual work of each neuron. Because I remember when I work in neural network, in a real neural network, that there is a process in the brain that is called the pruning. Pruning means that when a neuron doesn't work in the developed stage of brain, when a neuron doesn't activate too much, it will die. When some connection, not when some connection doesn't work, they will be quit off. And so my question is if in the field of a neural network, it does exist a technique of optimizing the neural network by studying the actual activity of each link.
Indeed, this is a huge field. For example, these are some standard techniques, but it's a very active research field. So, for example, some people propose dendrites to institute only nodes to generate modeling. So there are a lot.
Yeah, because I did a mistake. The pruning is not of a neuron, it's over a connection.
Yeah.
So it's a sort of reinforce the connection or quit out the connection if the connection it's unuseful.
Yes.
Something like that. Okay.
Yeah, the other thing here is that the main groups of research that are Google, NVIDIA, and anything have always the last word in the
Well,
in the development of the thing. So everybody use the methods.
Okay, thank you.
Yes.
Yeah, I have a question because all the training that you are doing for the radial velocity case, it's based on solar data,
Yeah.
but you want to extrapolate to other stars for which there will never be that much data ever. So how can you extrapolate or do apply these techniques into stars that are different than the sun, for example?
Yeah, well, that's why, for example, in this case, I mentioned that we test only with 400, etc. And it's working more or less well because it's a more realistic scenario. Okay, because of course in the sun we can achieve this precision because we have a lot of observations. But indeed, if we try to train a different model with only for a few hundred of samples, we can have a precision without considering the stellar activity and other things. But in principle, something similar to this hold-out approach, that we are around 25 centimeters. Of course, the precision that we achieve using the cross-validation technique, we use the 2000 of time stamps, so it's better. And of course, we are limited of the real data that we have. But if we split some percentage of these small data to the cross-validation, we need to analyze each particular case to see how can we recover. But in principle, the method can be is the same. Is the same. The method we already have some preliminary tests and.
Doesn't it depend on the chosen 400 spectra?
No, it's totally random. Yeah, because again, similar related to the previous question, we don't want ad hoc configuration, so we need to sample randomly everything.
So in the random selection for the convalidation, you use it like a program, or you use a random sample with repetition. So you have 400 spectra and you have like 200. If you use a tenfold cross validation with a repetition, maybe you can.
Yes, indeed, we forced to avoid that. So we select beforehand the splitting in order to have different indexes in each fold. Yeah, because if we do random selection on the fly, we can have the same training samples that in a previous test set, for example.
But you don't see increasing the fold with repetition, you can maybe
Improve. We tried with 10 folds. Indeed, in this case, we choose 5 folds because with this number, we can say that the holdout approach is a particular case of one fold of this other approach. So that's why we choose 5. But yeah, in the appendix, we analyze the 10 folds. Another question.
So
Yeah, no.
in the marks, you say that I believe if you use or if you are thinking to use a explainable model that can show you what neural mass developed in each signal, maybe you can explain a lot more using your physics knowledge to understand what is the information that you really need to enter the model. So maybe you have some word about that, or you
No, indeed not, because this I am not very involved in interpretable machine learning, but with neural networks, I am not sure if the classical methods for machine learning work properly because we have millions of parameters. So I don't know, but yeah, it will be very interesting to consider.
Because maybe we are getting a lot of information and a lot of this information is not used, yeah, it's gone out in the process, so maybe planner model teach you how to pick.
Yeah, indeed. It will be very good. No, thank you.
All right, we have no more questions, so let's wrap up then.
Thank you.